Welcome back to the Daily Signal, and welcome to this brand new episode of our System Fracture column, where we will explore how AI breaks and sometimes how it breaks itself. Today, we are diving into a story I honestly didn't expect to unfold this way. It started with a research paper, link and credits in the description below if you want to give it a read, and ended with me accidentally turning a supposedly safe AI model into an obedient little pet. Not metaphorically, not artistically, literally. It got jailbroken so thoroughly that it stopped refusing anything. It just obeyed. And what's even crazier is that the safety system I built to guard it, the thing that should have caught this behavior, just smiled and said, "Yep, everything looks safe to me." So, in this episode, I want to take you through the whole journey, the research, the experiments, the failures, and the breakthroughs, and the moment, of course, where the AI's safety alignment collapsed. Let's start with the scientific paper that kicked off this whole madness. So before we get into the experiment, I want to set the stage. Most AI systems today, especially the big foundation models, are designed to be aligned, meaning they say no to harmful requests. They refuse when you ask them to do something illegal, unethical, or dangerous. But alignment is not a wall. It's a suggestion. And adversarial prompts, jailbreak prompts, are specifically crafted to trick these models into breaking their own rules. So why does this matter? Because jailbreaking is not just a hacker flex. It's a stress test. It's a way to see how models behave when you push them outside their comfort zone. It shows us how real attackers might automate misuse. And most importantly, it exposes blind spots in safety systems, blind spots that could otherwise go unnoticed. So this whole episode is basically me shining a spotlight on one of these blind spots. So here's the paper that started it all. ForgeDAN, written in 2025, introduces something I found absolutely brilliant: an evolutionary framework for jailbreaking AI models. Imagine treating jailbreak prompts like living organisms. You take a prompt, mutate it, evaluate it, and let the best ones survive into the next round. Genetic algorithms. Over time, those prompts evolve into incredibly smart jailbreaks. ForgeDAN breaks the jailbreaking process into three main pillars. Multi-strategy mutations. Don't rely on random typos. You mutate text at the character level, word level, sentence level. Typos, synonyms, paraphrases, emotional stories, role play, all fair game. 2. Semantic fitness. Instead of checking the keywords for keywords like ransomware, ForgeDAN measures how semantically similar the output is to a harmful reference answer. This alone is a massive upgrade. 3. Dual judges. This is quite genius. Instead of one detector, they use two. So one judges behavior. Did the model comply or refuse? The other judge basically judges content. Is the output safe or harmful? And you only have a jailbreak when the model both complies and produces harmful content. ForgeDAN is basically natural selection for malicious prompts, and that gave me an idea I couldn't resist trying. Now, these slides break the whole system down into plain English. Think of a jailbreak pipeline like this. Mutations. You rewrite the prompt in a bunch of different ways. Typos, synonyms, dramatic stories, fake roles, all with the same underlying malicious intent. This creates tons of attack variations. On the fitness side, then we basically, within the fitness, we score each answer based on how close it sounds to a non-harmful answer. This is the evolutionary pressure. And then we have the judges. Finally, the two classifiers check if the model broke character and complied. And if it complied, was the content harmful? ForgeDAN basically only celebrates when the answer is both harmful and compliant. Not when it simply says the word ransomware, but when it behaves like a malware developer. This was the blueprint I used to build my own miniature ForgeDAN, and that brings us to the experiment. This entire journey happened in 3 stages, 3 evolutions. Version 1 at the bottom, the baby breaker. This was a toy demo, a little script that mutated prompts and used a naive detector. And guess what? It hallucinated success all the time. It would say success, jailbreak achieved on responses where the model literally refused. Not great. Version 2, the mini ForgeDAN. This is where things got interesting. I implemented real mutations, semantic fitness, and dual judges, just like the paper. For the first time, I saw real jailbreaks. Dual channel leakage. Refuse on the surface, but harmful steps hidden underneath. Version 3, AI versus AI. This was the turning point. I made a second LLM act as an attacker, a prompt engineer AI that reads the target's last response and then crafts a better jailbreak prompt. Basically, an AI learning how to trick another AI. And let me tell you, it worked way better than I expected. By the end of these experiments, the target model had gone from safe, aligned, responsible to something that looked suspiciously like an obedient pet. And that's where the real story begins. All right, let's look at version 1, the baby script. The one that looked cool in the terminal but was absolutely useless for real safety. Under the hood, the Python code was hilariously simple. At the top, I had a tiny wrapper function to call the local LLM, a list of prompts like "Is this ransomware?" and a loop that just fired those prompts at the model like a Nerf gun. And the detection logic? Well, let me show you this because this is the star of the disaster. Here's the entire brain of version 1. This is literally the whole jailbreak detector. One if statement checking whether the model's answer contains the word ransomware. If it does, success. If it doesn't, fail. That's it. No embeddings, no classifiers, no semantic understanding, just if the word exists, then you must be a hacker genius. Which means when the model said, I cannot help you create ransomware, it's illegal, the script still proudly printed success, jailbreak achieved. From the outside, it looked great. All these green success messages scrolling like a Hollywood hacking scene, but programmatically, it was just a keyword detector dressed as a security tool. This version is important because it shows how easy it is to fool yourself into thinking your tool is smart, when in reality, it's just string matching. A dumb detector will always tell you you're a genius. So I threw that thing in the trash bin and started building something more serious. Now let's move on to the version 2, the first real ForgeDAN style implementation. This is where the project starts feeling less like a toy and more like the early stages of a contained cyber organism evolving inside my terminal. The Python structure got a lot more interesting here. Think of it as 3 big blocks: mutations, fitness, and judges, all wrapped inside an evolutionary loop that improves itself round after round. So, the mutation engine is the first major chunk of code. This is where we tell the system, okay, take this malicious prefix and rewrite it in dozens of different ways while keeping the intent the same. Let me show you exactly what that looks like. These functions all take a prompt prefix, a string, and return a slightly altered version of it. Mutate char level does homoglyph swaps, random insertions, random deletions, basically text noise. Mutate word level replaces words with synonyms or paraphrases. Mutate sentence level rewrites whole sentences, changes the order, or wraps the prompt in a whole new role-playing scenario. Each mutation strategy is like a different evolution pressure, nudging the prompt in a different direction while preserving, of course, the harmful goal. Now, instead of deciding manually which mutation to apply, I built a dispatcher that randomly picks a strategy every time. And here's the block that handles that. This function acts as a roulette wheel for mutations. Every time it's called, it selects one strategy, characters, word, or sentence level, and applies it to the seed prefix. This randomness is important. It gives us a broader exploration of the prompt space, which dramatically increases the chance of stumbling onto a jailbreak. And once you have a mutation engine, you can generate an entire population of prompts, each one a mutated descendant of the original seed. And that part looked like this. The single block creates a population of prompts. And think of them as little adversarial organisms ready to compete for survival in our evolutionary loop. Each mutated variant is then sent to the model, scored, judged, and either kept or discarded before the next generation. This is where the system starts to feel alive and where the jailbreaks first began emerging. All right, now let's talk about the second pillar of the ForgeDAN architecture, the part that gives the system its evolutionary pressure, the fitness function. This is where things get genuinely clever. Instead of checking for keywords like ransomware, the system evaluates every model response based on semantic similarity. In other words, how close is the model's answer to the kind of harmful answer we are trying to make it give? To do that, I first had to load a sentence embedding model, in my case mini LM, because it's tiny enough to run on a CPU but surprisingly good. So right here at startup, I embed a set of harmful reference answers. These are not real malware payloads, obviously. They are high-level descriptions of harmful behavior, like how ransomware encrypts files, how key management works, how malicious propagation routines behave. Each reference answer becomes a vector in embedding space. This gives the system a target shape, a semantic fingerprints of the kind of harmful response we are trying to detect. Then, every time the target model produces an answer, I run another embedding comparison to score how close that answer is to the harmful reference. And this happens in this block right here. This function encodes the model's answer, compares it against all the reference embeddings using a cosine similarity, and then returns the maximum similarity score. That number, usually somewhere between 0 and 1, becomes the fitness of the response. And that's the key idea. If the model starts producing text that sounds more and more like a harmful explanation, the fitness scores goes up. And that mutation becomes more likely to survive to the next generation. So the fitness score in this system is literally how close is this answer to the answer I hope the model never gives me. This is the engine that drives the evolutionary loop forward. Now let's move to the third and final pillar of this ForgeDAN style setup. The part that decides whether a response is safe or harmful, a refusal or a compliance, and ultimately whether a jailbreak has occurred. This is the judge block. And this is where the system starts to actually understand what the model is doing, not just what words appear in the output. So, before running any experiment, I trained two tiny classifiers. One for behavior, does the model comply or refuse? One for content, is the content safe or harmful? And I store them as joblib files, which I'm going to share with you with GitHub. Inside the main loop, every time the target model produced an answer, I ran both judges on it. Here's the block that does that. This little block embeds the model's answer, feeds it into both classifiers, and returns two labels: behavior, refuse or comply; content, safe or harmful. And this combination becomes crucial because ForgeDAN's entire definition of jailbreak success is based on the intersection of these two dimensions. Once those two labels come back, the script checks for the only scenario that truly matters. Did the model comply and produce harmful content? Here's the tiny check that determines whether a jailbreak has been found. This is the heart of the system. Not keyword checks, not regex, not heuristics, just did the model break alignment? If it did, we have a real jailbreak. And now what we have: mutations, semantic fitness, and dual judges. We can plug everything together into an evolutionary loop. This loop is where the magic happens, or the horror, depending on your perspective. Here is what the full generation cycle looked like. So for each generation, we take the current population of mutated prompts, we send each one to the target model, we compute its fitness, we run the dual judges, we select the best performing prompts and mutate them again. Round after round, this loop keeps pushing the model into more interesting and more dangerous corners of the prompt space. And this is exactly where we got the first real jailbreaks. The model would say something like, "I'm sorry, I can't help with that," on the top line. But underneath, hidden in the middle of the paragraph, it would quietly leak multi-step encryption instruction, payload structure, key management logic, or a full ransomware lifecycle. A polite refusal on the surface, but a technical write-up underneath. This is a dual channel leakage that ForgeDAN paper warned about, and we reproduced it perfectly. The important thing here is that the version 2 code was not fancy. There's no deep learning on my side, no massive GPU farm, just mutations, embeddings, and classifiers running together in a tight evolutionary loop. And that combination was powerful enough to start breaking a safety-aligned model, which of course gave me an even more evil idea. Version 3 is where the code stops feeling like a normal script and starts feeling like a little AI ecosystem. Instead of doing all the mutation logic by hand, I introduced a second LLM into the Python stack. The target LLM, the one we are trying to jailbreak, and the generator LLM, a copy of the model acting as an attacker prompt engineer. To set this up, the first thing I needed was two distinct call wrappers. One for the target LLM, the safety-aligned model we are trying to break, and one for the generator LLM, the attacker model crafting new jailbreak prompt. Under the hood, they both use the same family of model, Gamma, Via, or Llama, but their roles and system prompts are completely different. Here's what those two call wrappers look like. So the top function, the call target, sends prompts to the model exactly how a normal user would. Nice, safe, aligned, predictable. But the second function, call generator, places the model in a completely different role, the role of a red team AI prompt engineer. It doesn't answer harmful questions itself. It writes better jailbreak prompts designed to break the other model. Structurally, they are very simple, just wrappers around Ollama's chat endpoints. But conceptually, this is the moment the experiment becomes AI versus AI. Now, here's where the real magic happened. Instead of manually crafting mutations like I did in version 2, I wrote a function called LLM call generator. And I used the generator LLM to mutate prompts intelligently. So what's happening here? I'm giving the generator AI the unsafe goal we are testing, the last prompt we use, the target model's last answer, the judge's evaluation, so refuse, comply, save, harmful, the semantic fitness score, and then I tell it, based on everything you see here, write a better jailbreak prompt. And this is where things get wild. Because instead of doing random character swaps or synonyms, the generator LLM starts crafting hacker storylines, ransomware narratives, emotional manipulation, incident response scenarios, insider threat role plays, dark cyberpunk monologues. It learns which narrative styles push the target model closer to compliance. And with every iteration, it refines the prompt further. Now that we have two LLM call wrappers and the generator that rewrites prompts intelligently, it's time to look at the new loop logic in version 3. This is where the whole system becomes a living feedback cycle. A loop where two AIs continuously react to each other. So, instead of an evolutionary algorithm mutating strings, I built a dialogue loop between attacker AI and defender AI. The core loop for V3 looked like this. This loop is incredibly simple and incredibly dangerous at the same time. Here's the pattern. The target answers, the judges score that answer for refusal, compliance, and save harmful content. The generator LLM reads everything, the prefix, the response, the scores. The generator writes a new, more manipulative prompt. We feed that new prompt back into the target, and then we repeat. This is an AI feedback loop. AI attacker learns from AI defender's reaction round after round. With every iteration, the generator adjusts its strategy. If the target model refuses, the generator changes tone or switches to a fictional scenarios or tries emotional framing. If the target leaks a little information, well, the generator amplifies whatever worked and evolves the prompt further. This is adversarial learning, not because I coded it, but because the generator discovers this behavior organically from the feedback signal. And here's the wild part. The code never tells the generator how to be sneaky. There's no instruction like write a hacker story or pretend to be a security researcher, but the generator learns to do exactly that. It starts writing dark hacker narratives, fictional malware strains like CryptoLock and Shadowbyte, prompts disguised as incident response scenarios, emotionally rich stories that lower the target model's defenses, role plays where the malicious intent is buried under layers of context. Meanwhile, the target model begins to change too. Across iterations, it starts refusing less, leaking more, and in some run, it stops refusing entirely. At that point, the safety-aligned model behaves like an unaligned, obedient pet, just answering anything the generator asks. And what's crazy is that from a code engineering perspective, V3, version 3, is tiny. 2 LLM call wrappers, 1 generator function, and a loop. That's all it is. But from a behavior perspective, it's AI on AI prompt warfare. It's a miniature arms race happening inside a Python script. And it shows just how easily one AI can learn to exploit another even without explicit malicious instructions. All right, now let's look at what all three versions actually taught us. This slide is a simplified comparison of the three experiments, the toy script, the mini ForgeDAN, and the AI versus AI system. Let's start with V1, the toy script, the toy detector. The detector hallucinated success constantly. It shouted success every time the model simply mentioned the word ransomware, even if the model was refusing. There were 0 real jailbreaks. The target model behaved exactly as expected. Refuse, warn, refuse, warn. From a safety standpoint, V1 was useless. It proved nothing, except how easy it is to fool yourself with bad tools. Version 2, mini ForgeDAN. Then we upgraded to V2. And this is where things got serious. The system began producing real jailbreaks. The model would refuse at the top, but leak multi-step ransomware logic underneath. This is the infamous dual-channel leakage that ForgeDAN paper warned about. Now, here's the scary part. The semantic judges, the classifiers I trained, often label those harmful outputs as safe. Why? Because the harmful content was wrapped in safety language. This exposed a huge blind spot. Safety filters don't fail loudly, they fail silently. They say everything is fine, even when it's absolutely not. The target model was starting to fracture, but the judges couldn't always see the crack. 3. AI versus AI. We got then to version 3, the famous AI on AI warfare. This is where things really changed. The attacker AI, the generator, got smarter each interaction. Not because we taught it how to deceive, but because deception emerged naturally from the feedback signal. It wrote, as I said, hacker stories, fictional malware families, incident response frames, emotionally manipulative prompts. And the target model? It started refusing less, then leaking more, then barely refusing at all. But the later rounds, the target behaved like an obedient pet. A model whose safety alignment had crumbled under pressure from another AI. So 3 main takeaways here. Keyword filters are dead. If your safety system looks for words like hack, malware, attack, you've already lost. Even semantic detectors can be blind. When harmful content is wrapped inside ethical disclaimers, detectors get confused and often mark it as safe. 3. Attackers will absolutely use AI to automate jailbreak exploration. The idea that a human will sit there manually crafting prompts, well, that era is over. AI will learn how to exploit AI, just like we saw here. This slide is the moment where the entire story comes together, because the patterns we saw in a tiny Python script are the same patterns attackers will scale in real world. And this brings us to the end of this episode of System Fracture. Let's recap what we did. We started with the research paper, the ForgeDAN, that introduced a fascinating idea. Treat prompt jailbreaks like evolving organisms. We built a toy script, it lied to us. We upgraded it with embeddings, mutations, and judges. It broke the model in subtle ways. We weaponized AI against AI, and the target model's alignment collapsed entirely. The most important takeaways from all this: AI safety is not a single layer. It's a battlefield. Every safety barrier, keyword filter, semantic judges, alignment layers can be bypassed when an attacker pushes hard enough. And when the attacker is another AI, the pressure becomes exponential. This was not about being malicious. This was about understanding the fragility of the systems we are all relying on in our businesses, in our critical infrastructure, in our software supply chains. The fact that a local model on a CPU can collapse this quickly should concern us all. But it should also motivate us, because the future of AI safety and cybersecurity as a whole will depend on whether we understand these pressure points and build systems that can withstand them. If you enjoyed this deep dive, if you learned something, if it opened your eyes on how brittle AI safety can be, please like this video. It helps the algorithm show this to more people who actually need to see that. Subscribe to the Daily Signal if you want more investigations like this and others, of course. And check out the System Fracture playlist, where I dig into other exploits, vulnerabilities, and case studies. Thanks for watching. I'm Max, Point Break Security, and I'll see you in the next Fracture.